So our plan for today is the following one. I will answer your questions from the homework if there are any, and then we'll continue our material actually discussing two more sections. They are both fairly simple, but first one is just a little review of the way how we handle sums. And with the experience from Calculus 2, probably it shouldn't be complicated, and then we'll do induction. Question? Okay, thank you. I keep forgetting that. Yeah, last time it was also second time I forgot it. Thank you. All right. Are there any questions from the homework? I don't plan to spend too much time because we have two sections to cover, but if there is something urgent, something that you are unable to find out. All right. By the way, before I forget, there will be a quiz on Monday, and that quiz will be on these two sections that we covered today. So nothing from Monday, but both things that we studied today will appear on our quiz. So there will be two problems. All right. So. Our first topic of the day is section 3.5, which is sequences and summation. Here in this course, we only talk about finite sequences. Why? Because if you want to talk about infinite sequences, particularly infinite sums, then we would need the limits, and that's a question that you analyzed in Calculus 2. But actually, analysis of finite sequences was probably missing before you started Calculus 2. So if you had this few techniques developed here, probably your Calculus 2, and the understanding of Calculus 2 would have been a little better. So first, what are sequences? So you can think of a sequence the same way as the order n tuple or array. But sometimes we think of it as different objects, so it's a good idea to keep them as two different objects. So here it is. Let's look at this object, 2 and 3. Did we already talk about this object 2 and 3, yes or no? What would that be? Ordered pair. So there are two objects. One of them is assigned to be first, and the other one is assigned to be second. But then we can think of this also in a little different way. And that is, we can think of this as there is a function that's kind of listing them. So you see, it will do basically the same job, but just in a little different type. So what would that be? First and the second. So who's first? 2. Who's second? 3. So here is the spot or index, and here is the value. Instead of writing this, we often say the following. First member, A1, is how much? 2. How much is A2? A2 is the 3. So that's what sequences are. So sequences actually list certain numbers, assigning values on spot number 1, spot number 2, and so on. So generally there, we had the following sequence AM plus 1, and so on, and at the end we have AN. So sequences do not need to start with A1. They might start with some other member, and then they can have different lengths. So for example, we'll say the following. A7 equals 10, A8 equals 15, A9 is 13, A10 is 4. So here is one sequence, and then we say what? It is sequence of length 4. First member has rank index 7, index 8, 9, and 10. So here are the indexes, and then you also have the values of the members. So here we have certain sequence where we know the placing of the member. It is placed on number 7. Why number 7? Because there might be that we were doing something else, and the other 6 places are occupied. So this is on position number 7, and has value 10. Position number 8, value 15, and so on. All right. Then something that's, I don't know, sometimes emphasized too much. It's not that important very often. And that is, sometimes you see a sequence and you want to write the appropriate formula. So how would you write the formula for the sequence that I just wrote? So what would that sequence be, example? You have a sequence -1, 1/2, -1/3, 1/4, -1/5, and so on. This one we want to be infinite sequence. So to the contrast, just something that you maybe saw in your Calculus 2 course. So what do we do here? We want to decide what will be the position for the first one. And usually that position is called either A1 or A0 sometimes. But let's say that this is position A1, and this is A2, this is A3, this is A4, A5, and so on. When you write it like this, then you see how that number n appears. So how does it appear? Yes, it appears in the denominator. So for every an, obviously, whatever the index is, that's the number in the denominator. There is 1 there, and there is one more thing to fix. What is it? Yes, that alternating, and you remember from Calc 2, it will be -1 to the n or to the n minus 1. That's never, we are never sure about that. The best way to check it is I'll try n, and then I will see if that matches the description. Otherwise, I'll do n minus 1. So when n is 1, what do I get? 1 over 1. -1 to the 1 is -1. Does it match? Yes, it does. So that's what we're going to do. Now, we want to talk even more about summation formula. So let's analyze the following example. Sum. So summation formula looks like this. There is a summation symbol, and there is a running variable. And that running variable has the limits the same way as definite integral. So a running variable is I, and it goes from 0 to 3. And it's a 1 over 2 to the I. So what is the meaning of this notation? It means, so this summation symbol says you will do pluses between the values that you calculate, and you keep running the values. I equals 0, then I equals 1, I equals 2, I equals 3, which is your last value, and you plug in each of them. So you get 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 squared, plus 1 over 2 cubed. So what do we get at the end? Whatever that is, so that would be 2 to the 0 is 1, so it's 1 plus 1/2 plus 1/4 plus 1/8. How much is this? 1 and 7/8. True. Very good. One of the things to notice, and I think we use this in the explanation of bound variables, so it's a good idea to connect it again. This variable I, is this free variable or bound variable? It's bound variable. That means it doesn't show up at the end. At the end, we get a number. So I is just the running index used to help you, just like a counter, to help you to organize the numbers to plug in. And when it serves the purpose to run from the lower limit to upper limit, it completely disappears, and there is no result there. But can we do the following? We'll talk about this more later on. Let me do this. I goes from 1 to m, 1 over 2 to the I. What happens here? So I is I bound variable or free variable? Bound the same way as a minute ago, because that's your variable of summation. It's a counter. But what is your free variable here that at the end has to show up in the result? What is it? M. Because I'm not disclosing here how far do I want to go. But basically, what does this stand for? It stands for 1/2, because I start here a little later, plus 1/4, plus 1/8, plus 1/16, plus 1 over 2 to the m. Last one is 1 over 2 to the m. And then here are those dots that are a little dangerous, because they assume that you are running through them, and of course I cannot write all the members if you don't disclose my m. But when you write things with the dots, here is the problem that we'll encounter very often in that section about induction. So, for example, if m is 1, no, if m is 2, how much is my sum? So sum I goes 1 to m of 1 over 2 to the I would be what? 1 over 2 plus 1 over 4, and that's 3/4. Do you agree with me? How about sum? When I goes from 1 to 1, 1 over 2 to the I. If I look at this developed form, and that is where people make error very often, they say the following. Do I have 1/2 in the beginning, yes or no? Do I have 1/2 at the end as well? So should I repeat that 1/2 or not? No. And that's what I see very often when people plug it in looking at those dots. They put m equals 1, so they have 1/2 in the end. They see 1/2 in the beginning, and they write it very often as 1/2 plus 1/2. That's wrong. Do you agree? Why? Because this is just generic writing, and it says when m is undisclosed, it says start here and end here. But that assumes that you have more than one member. If you have only one member, what do? Are those two the same thing, yes or no? I write first one and stop immediately. So there's no second one. This is just 1/2. So making sure that you properly understand this notation when the dots are written. Don't count both of them. Just last one is assumed if m is greater than 1. If m is 1, that means just write the first member. And then, by the way, we can summarize this, but that's not our goal today. All right. Let's skip this. Let's look at the example 355. So how would you write this in the sum notation? So if someone writes the open form, example 5. So someone wrote this, 2 squared minus 1 plus 3 squared minus 1 plus 4 squared minus 1. How would you write this in the sigma notation? So generally, each of them looks like a square minus 1. Do you agree? So square minus 1 is fixed. Who is changing? Who is running? The base. So your base I or j, that's a standard 1. And then you just need to record what is the first value for I. So what is the first starting value? And what's the last one? So recognize the pattern of the member in the summation, and then write that pattern, and then count the starting and the stopping value. So as I said, these are all fairly simple things. By the way, something that you maybe never saw in probably calculus 2, besides sigma notation, there is a p notation, and that one does not sums, but what? Products. So if you have a product, then you also use p notation. So it's this is letter P for products. Yeah, that's capital pi, I think. And so in this case, it would be the same thing as a minute ago. The only difference, you don't write the sum. What do you write? Letter P, and then indexing goes the same way. By the way, how comes that you never studied infinite products in calculus 2? Did you?
No.
Why not?
There was only one product?
I'll say, no, but sometimes people do infinite products, and they use them for all kinds of representations. So it is something that's used in mathematics.
You could just
But
do it as an infinite sum.
why? How could it be? This is
It's just addition.
Oh, but yes, but how do you? I like what you said, but your second proceed didn't work that well. So what? If I have A1 times A2 times A3 times AN products, and then if I have infinite product like this, so product of AI when I goes from 1 to infinity, then what can you do? Take ln of this one. So what will that make out of this ln? Ln of the product is sum of the ln AI. So generally you take ln's of the product and you do summation series that you studied in calculus 2. So if you ever need to look at the convergence of the products, just take ln, and then you can use all those criteria. You remember all those tons of criteria you had in calc 2? What was it? Anyone remembers? Like member test and what else? A ratio test and a root test and integral test and alternating series test and all that. Although you cannot do for products that, because if it switches the sign, then you'll get what? ln of negatives does not exist. But the same way as it's important for series, if numbers positive or negative, here is important if it's bigger than 1 or less than 1. 1 is the threshold because ln 1 is 0. Anyway, this is just a little digression. So there is a way to avoid products if you take ln and make them into sums. But sometimes it's more elegant to work with products. So I just included it here so that you are aware if you ever see this. Oh, here's one product that's extremely important, and you dealt with it in your calculus 2, and we'll deal with it in this course as well, and that is factorial. So how can you elegantly describe the factorial? So factorial is what? So what is 3 factorial? 3 times 2 times 1. What is 5 factorial? 5, 4, 3, 2, 1. And you can calculate it. So how would you describe n factorial? So product of all these numbers. So you can say product of all the numbers I. You start with lowest one is what? 1. And the highest is what? Your n. Who's your variable here? I or n? N is your variable, and I is just the running counter bound variable. At the end, I doesn't show up. Who appears? N, because that's what you change. Once you fix your n, you just do the calculation. So factorial is a really special type of the product, yes?
Does this work if your I and n are both 0?
Oh, that's interesting. Yeah, so what? So 0 factorial is equal to 1. That's convention. Although in mathematics, remember, empty sum is always 0. Empty product is always 1 because, whenever you multiply, you get 1. By the way, and this has modeling a reason. What is it? You remember factorial is how many ways you can shuffle objects. You saw that in combinatorics. Like, what is 3 factorial? In how many ways can 3 persons sit on 3 chairs and shuffle around? So what is 0 factorial? So if I want in how many ways you can shuffle on your seats, it will be 30 factorial or whatever your number is now here. But what would 0 factorial represent? when we finish the class and we all leave, in how many ways can I arrange the seating? In an always or in one way? One way, empty room stays empty room, no shuffling, but still exists. So configuration exists, so model-wise also makes sense. So 0 factorial equals 1. But here's another question that you can ask. How much is 1/2 factorial?
Can you use non-integers?
What's it?
Can you use non-integers?
Yes, you can. Mathematicians think of every opportunity to do everything a little more generally than.
Is it 1 factorial over 2 factorial?
What's it? Sign up for your differential equations class. There is a gamma function, so it's called gamma function that generalizes factorial for any, not only fractions. You can get pi factorial or whatever real number you want, and that generalization is called gamma function. And then we mention it briefly when you do Laplace transformation in DE class. So, and we calculate exactly how. It's square root of pi over 2 or something like that, I think. 1/2 factorial is square root of pi. No, this one is something like square root of pi over 2 or something similar. And there is a reason why it's all that. So theory of factorials was generalized to non-integer values. Anyway, so this is just reviewing of all these little tricks. Example 8. How much is 6 factorial over 8 factorial? You had to deal with this very often in your calculus too. What did you do in this case? By the way, we'll need it here later on in chapter 4. Yeah, so how do you do this? So you keep your 6 factorial there, and you go 8 factorial is 8 times 7, and all the others are basically 6 factorial. The one that starts early, you develop first few members, and then these two are the same. So it's all 1 over 56. So the one that's stemming out is developed until it matches the lower one. And remember this trick in Calc 2? When you look for the radius of convergence or something like that, this happens very often. And here is something that probably you haven't seen before. So this is the only maybe new thing, and that's something that I will ask you on the quiz. What is this? If you have sums, and we will need it for some, but not for this one, for D class, I will need it on Monday actually. So sometimes you don't like the limits in your sum. For example, they are not alike or something like that, and you want to change the limits, so how do you do it? So instead of telling you the story, I'm going to do it in a particular problem. So here it is. Example 9. I have the following sum. Sum k goes 3 to 10 of k over k squared plus 4. And I don't like that it goes from 3 for whatever reason. I'd like it to start with 1. So someone left me this in some calculation, and I say, no, I don't want my counter to go from 3. I'd like it to go from 1. Can I do it? Yeah. The answer is yes. How?
K plus 2.
So, yes. So generally you do the same thing as change of variable in the definite integral. So, so what? I'll do it once, and then I'll tell you the shortcut. So if k goes from 3, I will introduce new variable, let me call it I, and I will be k minus 2. So what happens now? And then if you remember definite integral, do you change the limits, yes or no? So what are the limits for I? Lower limits, when you plug in 3, 3 minus 2 is what? 1. And upper limits is what? 10 minus 2, which is 8. So now it goes sum. I goes from 1 to 8. But then, instead of k, what do I write? You need to solve, like in integrals. I plus 2 equals I plus 2 over I plus 2 squared plus 4. Here it is. Is this how we do it? No. I did it just once. There is a shortcut to this. I wanted you to see it once, how it really works and why is this accurate. Basically, we do it automatically without all this writing. Did you copy this? Okay, can I raise the size? So here it is. Here's what we do. Usually we say the following. And I don't even change the letter I. I'll call it K again because it's bound variable, so it doesn't matter really. So what happened? In the expression, what did I do with K? Did I go up or down? Up. Instead of K, what do I have? K plus 2. So in the expression, you go up, but on the limits, where do I go? That's it. So if you want your limits to go by 2 down, go down, both of them, but here instead of K, go up, K plus 2. And that's how I do it automatically without all this writing. Because sometimes we need to do it 4 or 5 times in the same calculation, so who's going to do all these changes of variables and everything? So in this time it happens what? Indexes went down and the expression went up, always in the opposite direction. And here is one example that illustrates why is this useful. Couple of cases where we want to combine expression. My question is, can I combine these two expressions here, these two sums, yes or no? The only problem is that there are those numbers in front of them. So what should I do? Distribute, and then when I distribute, my main concern is, I ask 2 things. Are the limits the same, and is the variable the same? So variable is the same, it's K, but limits must be the same because then I can add them member by member. So generally what? Example 10. If I have 2 sums of 3k squared plus 4, k goes 1 to n, plus 5 times sum of 2k squared minus 1, when k goes 1 to n. Then what do? I distribute inside, k goes 1 to n, 6k squared plus 8. And the second one says sum, k goes 1 to n, 10k squared minus 5. And this would be sum, k equals 1 to n, 16k squared plus 3. Here it is. So the only trouble here that we had was these numbers ahead of it. So we got them inside, distributing, everything worked just fine. So this was quite trivial operation. But let me see something more challenging that looks like a quiz problem.
Does the upper and lower limit have to be the same?
Yes. Here it is. Here is something that you cannot do. So the problem is, and let me actually change it a little bit. Yeah. Let me change problem. So it's 11 example, 11 star. So it says the following. Sum k goes 2 to 10, 2k plus 1, plus sum k goes, I'll do the different example from this one, from 4 to 11. Are they again practicing that shooting training? All right, here it is. We have lots of troubles here. Even it's worse than what you have there. Why? Because look at the example that's on the screen. You see that the difference is 8. So if I shift by 1, they will match very nicely. But here I have even bigger trouble. Here there is a span 8, and here the span is 7. Do you see? So no matter what I do, they will not match.
Make it work.
So what shall I do? Let me get this guy down first, so that they start at least on the same spot. So what do I get? Sum K goes 2 to 10, 2K plus 1. And now I'll say the following. I want to go down, so it goes from 2 to what? 9. What about this guy? It goes 2 up. So what would that be? Just K. Do you understand the move? That's exactly the shift that we discussed a minute ago. So that's good. At least they start on the same spot. Unfortunately, they don't end on the same spot. And I cannot do whatever I do with the shifting, they will not have the same length. So what can I do then?
Write the last term of the first.
Exactly. Separate this one. What can I do? So how much is the last member when K is 10? How much is this? 21. So I'll do 21 separately, plus sum. K goes 2 to 9, 2K plus 1. Plus sum, K equals 2 to 9K. Do they match now, yes or no? Yes, there's 21 on the side. That doesn't matter. K goes 2 to 9, 3K plus 1. Here it is. So you match at least one of the limits. If the other one doesn't match, those few extra members, just push them on the side. If I didn't want to do it that way, you know what else I could have done? So these are options. So what is their overlap? Is there overlap between 4 and 10? Yes or no? So do both of them without shifts at all. Do overlap between 4 and 10, and then write a few members here, a few members there, and again you have, so you have some options. So whatever suits what you need. Yes?
If there's like too many numbers that are not on the overlap, could you instead separate them into two different sums that you like?
Yes, that might be, yeah, so see. So as I said, be creative on it. So here are a couple of tools and make it look as convenient to you as you can. That's the idea, nothing general, like there is only one way to do this. So there is a shifting, and then there is that extra few members trimming on the side, and basically these are the ideas. That's it. That was section 3.5. There was really not much, just those things that you already saw before, a couple of details. And it's actually a little too early to make a break, but I suggest to do the break now. We never made break early, but this time it will happen. And then we start 2:25 to do the induction. That's much more important thing. So 2:25 is when we continue the second hour.